Hi, I'm Julian. I'm a PhD student in the AVS lab at CU Boulder, and today I will present some of the work we've done about the electric potential estimation of inhomogeneous and differentially charged objects using X-rays. So spacecraft charge naturally in orbit due to various currents. For example, you have energetic electrons and ions in the local plasma, and as these particles impact on your spacecraft, they will provide a current to the spacecraft. And another current, for example, is the photoelectric effect. So incoming photons from the sun will excite electrons in the surface material of your spacecraft. And as these electrons leave the spacecraft, they also provide an electric current. And these currents generally depend on a lot of factors. For example, they depend on the plasma environment itself, which changes with space weather conditions. But the currents also depend on the spacecraft shape and the material of the spacecraft. So as a result, the currents and spacecraft charging in general is pretty difficult to model. So if you care about the electric potential of your own spacecraft or neighboring spacecraft, you essentially have to measure the electric potential. And the one approach to do this for a neighboring spacecraft is to use X-rays. So that's what we refer to as the Xray method. And the way this method works is that you have a servicing spacecraft with an electron gun, and that electron gun is aimed at the target object, so the object whose potential you're trying to measure. And as the electron beam travels from the servicing spacecraft to the target object, the kinetic energy of those electrons changes, and that change in kinetic energy corresponds to the difference in electric potential between those two spacecraft. So that means if you are able to measure the electric potential of your own spacecraft, and you know the initial energy of the electron beam, which corresponds to the operating energy of the electron gun, and if you're able to measure the landing energy of the electrons as they arrive at the target, you're able to infer the electric potential of the target. And the way we measure the landing energy is by looking at the X-ray spectrum that results from the electron beam impacting on the spacecraft, because X-rays are only emitted up to the landing energy of those incoming electrons. So by finding the maximum photon energy in the recorded spectrum, we can infer the landing energy and therefore the electric potential of the target object. So in our experimental setup for this work, we look at complex shapes. So we have a spacecraft bus, a cube, and to that cube we have two panels attached. And all these three components are charged to different potentials, and they're made of different materials. So the spacecraft bus, for example, is made of aluminum, and one panel is made of copper, and the other panel is made of titanium. And we control the potential, so the voltage of each of those components with high voltage power supplies, so the potential remains constant throughout the experiments. Another note on the experimental setup is the beam steering. So our electron gun is capable of steering the beam, and that allows us to essentially deflect the beam in a way that we can hit different components of that target object without changing the orientation of the target object. So here are some X-ray spectra shown for different beam deflections. So on the top left, we have a deflection of negative 300 volts of that deflection grid inside the electron gun. And that essentially deflects the beam to the right. And it deflects it actually so much that the beam is impacting on the chamber wall. So we find characteristic X-ray peaks at 5.5 and 6.5 keV, which corresponds to chromium and iron. So that indicates that we're actually hitting the stainless steel chamber wall. And if we deflect the beam a little less to the right, so for example, for negative 90 volts on the deflection grid, then we will hit the copper panel, and the copper panel is charged to negative 1000 volts. So what we find here is that if we use a 12 keV beam energy, and the copper panel is charged to -1 kilovolt, then the landing energy of the electron beam is about 11 kV, and that's what we see with those blue estimation lines in the top right plot. And similarly, if we deflect the beam by, if we use a deflection of 0 volts, then the beam is pretty much straight, and the beam impacts on the aluminum cube, and we measure -5 kilovolts of a potential for that object. And if we deflect the beam to the left, we are measuring the potential of the titanium panel, which corresponds to -3000 volts, or in this case a landing energy of about 9 keV, because we're using a beam energy of 12 keV. So these are the results for the different amounts of deflection that we use on the deflection grid. So depending on what deflection you use, the electron beam will impact on a different component, or maybe even the chamber wall, and you measure the potential of that component. Now, something that is of interest to us is how we can measure multiple potentials simultaneously from one single spectrum. And to do this, we look at here in theory about how this would look in a total spectrum. So if you have two, if your electron beam impacts on two components, then the total X-ray spectrum is a superposition of the two individual spectra. So one on the left here, for example, with a landing energy of 10 keV, and another one with 7 keV, will result in the total spectrum shown on the right, where we have a deflection point corresponding to that second potential. Now, this deflection point is pretty hard to identify in the spectrum with noise, so our approach is to measure one landing energy from the total spectrum, so in this case 10 keV, and then we generate a theoretical X-ray spectrum with a landing energy of that first estimation, so 10 with a 10 keV landing energy. And then we subtract that theoretical spectrum from the total measured spectrum, which gives us a residual spectrum, which should correspond to the individual spectrum generated from that second component. So ideally, that residual spectrum in this example would have a landing energy of about 7 keV. And that's what we did here for 3 steps, because we have 3 components. So in the top row, we have the spectrum that we use to estimate the potential, and in the bottom row, we have the residual spectrum that we get once we subtract the theoretical spectrum. So basically, in the first estimation, we estimate the landing energy here about 11 keV, because we're measuring that highest potential corresponding to -1 kilovolt, or a landing energy of 11 keV. And then we subtract the theoretical one from the measured spectrum, which gives us a residual spectrum. And then we use a new residual spectrum in estimation 2 to estimate the potential again, giving us another residual. And then we use it again and again. And in the end, ideally, we would have a spectrum shown in the lower right that is basically just noise. So there is no other signal present, basically. And these are the results for the various estimations. So in the first estimation, we measure the potential of the copper panel corresponding to -1 kilovolt. And in the second estimation, it already gets less accurate, because we're dealing with much noise, and the second estimation depends on the first estimation, and the subtraction of the theoretical spectrum from those measured spectra will also yield some inaccuracies. So what we found in this work is really that if you have so many components and potentials inside one spectrum, then you might be able to identify differential charging. So you might be able to identify that there are 2 potentials, but you're not able of measuring both potentials or 3 potentials accurately. So those are really the conclusions as well, that the estimation becomes more inaccurate with every step, and also that the characteristic peaks are sometimes a problem. And with that, I would like to thank our sponsors, and please feel free to reach out.